zjeść shumë probleme. Okay. So here we have the thing. I think the camera is on. Okay, the class is joining. Okay. So for today, wait a second. Okay, I think I left my notes in the class, but it's okay, in the office. Okay, so for today, what we are going to see is that we are going to cover a couple of examples where we implement some simple algorithms of how to enhance the specific image. So, and one small reminder would be that we use filters, okay? And the filters, we apply them in the real domain and in the transform domain. So I think we know this, right? So let's consider that this is real domain, and this is the transform domain. And with transform domain, the most common transform domain is the Fourier domain, and we already know this. And let me adjust a little bit the settings. Go. Probably the quality improved slightly. Okay. So we are in the real domain and in the transform domain. And in the real domain, we can apply low-pass filter, and we can also apply high-pass filter. Also, the same thing, we can do it in transform domain. We can apply low-pass and high-pass. Okay, so this is high-pass. So we already know these. And for example, in the real domain, we had median filters or Gaussian filters where we convolve or we do an element-wise multiplication of all the pixel values with a kernel, okay? And this kernel was, for example, a 3x3 matrix or 4x4 matrix, which tries to extract different features. Now, so this is high-pass filter, low-pass filter. So this high-pass filter, in principle, it's always equal to 1 minus the low-pass, okay? So this is how we can mathematically write this one. And when we consider the real domain, we have the domain, which is x and y, okay? We have a domain, which is denoted as x and y. And in the transform domain, we have the new domain, which we denoted as UV. Okay, at least in this course, we denote it as UV. So the reciprocal of x is u, and the reciprocal of y is v. So here we have the coordinate u, and here we have the coordinate v. And the low-pass filter, it's a filter which is going to allow the low frequencies. How does it do this? It multiplies. So let's continue this like this. We know that it multiplies with 1 the low frequencies and multiplies with 0 the high frequencies. Okay, this is a low-pass filter. And when we talk about a specific image, just for a moment, let's consider that this is the real domain, and in the transform domain, we know that all the information is centered with respect to 0. So this is the point 0, 0, right? And then I'm afraid that okay, probably this is slightly better. And we know that in the Fourier domain, all the frequencies, they are written down with respect to the 0, 0 point, which denotes the lowest frequencies. And normally, whenever we get any random image, the most dominant features, they are the 0 frequencies or the frequencies which are very close to 0. Okay? So most of the information, it's right here. Okay? And then, if we also, and we know that high frequencies, they mostly correspond to the noise. So the highest possible frequency is a noise, right? And the highest noise is a subsequent change between 2 pixels, which would be 0 and 1. And in the next pixel, it still changes. This is the highest possible noise frequency. And then, so if we want to get the image clearly, we have to multiply with a filter, which is low-pass filter, right? But sometimes we want to enhance the edge information. And the edge information, it contains the high frequencies. So for this reason, we can apply, instead of a low frequency like this, we can apply 1 minus LP, and 1 minus LP, it's 1 everywhere, and 0 at the center, okay? So this is the inner end, this is the high-pass filter. So this domain is 1, I think this much we know, but when we do this construct, what we are doing to some degree is that we are multiplying by 0 the lowest frequencies, right? So that's not the best possible thing to do. And for that, we often do also this other, we do so instead of this one, we can lift. So let's assume that initially, so this is the z-axis, where we denote the intensities of the filters. Imagine for a moment that we can do a rescaling. Okay? So we can lift up this filter by some value k1. Okay, so this means that we are not going to multiply with 0 the lowest frequencies, because if we do that, we lose the major components of the image itself, and we just preserve the edges. Okay. So what we can do is that we can lift this a little bit higher, and in this filter, then this new expression for the high-pass filter would be the following: high pass would be equal to some constant k1 plus 1 minus LP. Okay, 1 minus LP. So this is what we can adjust the high-pass filter, and let's do this with H star. And now we know that this high-pass filter with a star, this is in fact, this is also denoted as K1 plus the traditional high-pass filter. I can write this one HP. But we can modify this a little more, such as we can add more components of the high-pass filter, and we can write this new expression as K1 plus K2 times this high-pass filter. Traditional. Let me write this one traditional high-pass like this. So what we are doing here is that we have an image. We transform the image in the transform domain in here. Then this whole image. So let's assume that this new filter now, we multiply this one with f, which is a function of u and v, right? This is the Fourier transform of the image. And then this whole term, now this is not equal anymore to the high-pass filter. So this was the filter modified, which was lifted a little bit up so that we don't destroy the low frequencies. And we can adjust this k as much as we want to add more component of the high frequencies. So we are here in the Fourier domain. Okay? Then we multiply with the Fourier representation of the image in the Fourier domain. And to all of this, we apply the inverse. Let me use a different color in blue. So we multiply this whole thing term in blue, and we take the inverse Fourier transform, IFT. We apply the inverse Fourier transform, and this is the image which is the improved image. Okay. So here, probably I didn't use very well this part of the board, but I think explaining this one step by step, we conclude that an improved version of the image would be equal to, so let's assume this was image initially, and this is the F, and this is image XY, and this is the FUV, okay? And FUV, it is, we know what it is. F as a function of UV is equal to the Fourier transform of I, of the image I, okay? So what we do, we have this Fourier transform, we multiply with this adjusted filter, and we get the improved version of the image. Now, we use this, so just for a moment, we are kind of going back to a few sessions in this class where we discussed about the Fourier transforms and the modifications that we do in the transform domain. Now, today, we are going to talk about the feature or feature descriptors. And these feature descriptors, they can be obtained similarly in the real domain and in the transform domain that we talked just here. So now we are applying filters in real domain and transform domain. And again, actually what belongs to this real, we can extract here, probably it's best if I write it here. So we can extract features of the images in the real domain and in the Fourier domain. So we call this descriptors, signatures, and so on. And now, one of the, we'll go to the examples, but for now, I want to write a couple of notes here on the board. So probably I may need to use this part here. This high pass filter, it was equal to 1 minus low pass. Okay, it's mathematically this is how we write it. So for the low pass filter, you can just draw a Gaussian function that looks like this, with a height of 1, minus 1, you get high pass filter. Now, let's go to the feature descriptors. One interesting signature feature is, for example, to describe the boundaries. So we are here in the real domain. And when we are in the real domain, we can write all of our boundaries as a signature with R and theta, okay? So this means that R and theta, that means that you give the radius and the angle theta. For example, if we have a circle, then we can observe, we can set a center, let's say that here is the center, and we have to write down what is R as a function of theta. For example, if we put the center here, then we can say that the radius at angle equal to theta, sorry, equal to 0, the radius is R, let's say 1.2. If the radius is 1.2, then the radius is here. Then if we increase the angle a little bit, the radius is still 1.2. If we increase the angle more, as we change the angle, so this is theta, this is measured in radians or degrees, but then it looks like this is the graph, okay? Or this is the feature or the descriptor for this circle. So we're going to get such a relationship where R is a constant as we change the theta. Now, if the figure is something like this, then if we try to draw the same thing, we know that when angle is 0, we have a distance. What is the distance R? Is a small value. Okay. Then, as we are increasing the angle, this is going to increase. Okay. Then, at an angle of pi over 2, this is a larger value. Then, when the angle is pi over 2, it goes to this distance. Okay. So these are some descriptors which describe how the boundaries of an object can change. Now, so this is something important. We talked about the features in the real domain, and we can observe something that if we rotate this circle, the features in the real domain, which can be described as a function of R and theta, this will not change, okay? But if we rotate this square, this image, so we can have an image that we rotated by some angle, we're going to notice that the descriptor, which is shown there in blue, is going to change because the distance or the R will not be minimum when the angle is 0. It's going to be minimum at some other value of theta. So it will be like a shifted sine and cosine with respect to each other. So I don't know, it could be something like this. Okay? So this would be the descriptor. Then, if we have two squares, one rotated with respect with some angle with respect to the first one, if we find these descriptors, we can observe that something is different, which would be the angle. So in this case, it looks like we have descriptors which are variant under some translation in space. So if the object is rotating, also the descriptor is rotating. Similarly, we have also descriptors which are rotationally invariant. Okay, and often these are much better than the previous ones. So here I can keep this part. When we discuss about the filter, I can write part of this one once again, which was that the high-pass filter with the star is equal to K1 plus K2 times high-pass filter. Then we talk about these descriptors or feature vectors. And now we have also feature vectors, which are, so let's say, for example, we talk about these, but apparently we have one category which are, let me put one rotationally variant. But we have also some other feature vectors or feature descriptors which are rotationally invariant. If we care about the orientation of an object, we may want to use this typology of features, okay, that can distinguish between two different angles of a certain object. But if we don't care about how the object is located in a big image, so we can have a lot of objects in an image, but we don't care how they are oriented, we may go after a feature descriptor which is rotationally invariant. Or we have also feature descriptors which are size invariant, which means that we can have a small object or a large object, but it's the same object. Let's say it's a small tree and a big tree, and a feature descriptor which is size invariant can be a good choice to go and track down where the trees are in the object. Some of you in the project that you have worked on have dealt with these feature descriptors or objects which can be large or small, and some of you might be a little aware of what we are talking. So now, in terms of some small theoretical aspects, this would be what I can use on the board. Now, let's see. Okay. Okay, so let's start with so let's read some. Let's read an image, and this image is the X-ray of a chest of someone. And now this is an image. It looks like it's a grayscale, which means that the pixels are from 0 to 1 in different shades of gray. And let's see this image that we just read. What are the typology of this image? It's like 503 by 720, unsigned integer 8. So the maximum value that this can have is 222. Apparently, it's not 255, which would be the maximum, but probably the minimum value of each column of I. Apparently, it's 3. It's not 0, which the boundaries would be between 0 and 255. That's good. Now, this is the image I. Now, let's scale this image from 0 to 1. So this means that we have the image from 0 to 1. We scale it in such a way. And now, this is image 0 to 1. The type of variable is double now. let's see what is the size of this image. We knew this one, it was 503 and 720. And now, let's try to construct a filter, but since we want to use padding, we want to construct a filter which is twice the size of the image. So if the image was 503, 720, we want to produce a filter which is double in size, and this 70 is a parameter of the Gaussian filter, which is the width of the Gaussian filter. Okay, so if you change the 70 in some other values, you're going to get some other parameters. So let's construct this filter. If you want to see how this filter looks like, this was not good. Okay. So this filter, we know how it's we know more or less how it's going to look like. It's going to be 0 in the middle and ones elsewhere. Okay. So this is our filter. Okay, so in the center, that's what it is. And we can also notice that the filter is twice the image size, because here we have dimensions of 1500, which is the largest, twice the largest size of the image. So it's okay, so this is the filter. That's good. And now let's convolve in the Fourier domain the image and with this filter. And we get this image, which was from 0 to 1, high-pass filter to 1. We calculate it, and let's see what the image will look like. So this is the image of the chest, or X-ray of the chest. Okay, so this was the original one, and this is the new one. Now we notice that some of the edges are still there, but we lose. Actually, what do we gain? That's a good question. We can check actually that here in the edges, where I'm going after with my mouse, we can see, it looks like we see much more of the ribs, okay, of the chest. And let's see how we can try to improve them more. Now, one reason why we may have lost some features, is that we have a high-pass filter that is multiplying with 0 the low frequency components. So because this one, it is 0. So let's try to, so this is the filter. So I'm trying, so this is really at the 0. So that means that we are losing the low frequencies, which means that we are losing the image because the highest frequencies are down there. Then let's try to lift this up as we wrote this on the board before a couple of minutes. So let's use a K1 0.5. So let's denote what is this K1 and K2. And this H1, it's here. Evaluate the selection. And here, let's have here figure 21. Plot this new filter, which we denote this one as H1. And this new filter, it's here. So figure 21, this was the original one. I think it's all predictable where this one is going to hover. So here we have it. So we can see that this is, it starts from 0.5. It doesn't start from 0 like this. So we hope that for sure it's going to be slightly better. But we are also adjusted the K2 0.75. So we want to use this coefficient when we add the frequency terms. So with this, let's see, evaluate selection with this filter and evaluate this feature. Let's see, and now let's not forget, we had initially, we don't need this and this for a moment. So initially, we had this image of the chest. Then we applied the high-pass filter, we got this, okay? And this does not look very well, but after we adjusted the high-pass filter a little bit, we get this, okay? We get this, this information, which is slightly better for reasons that we just mentioned. And now that we have this variable, that after we apply this filter, this is a double variable, and its values are not, so if we check here, what is the maximum value of the I, which was from 0 to 1, high pass filter 2. Is this the correct? So I'm trying to get high pass filter 2. So it's 0.45. Okay, so we can scale this up between 0 and 1 so that we can improve this slightly. And we can use this scaling function. Then if you want to see this one, how it looks like, the new version it should be closest to this previous image. Okay. Now the pixel values we just have stretched them a little more, which now, if we see here, the maximum value to 0.45. But now that we stretch it up, this maximum, it's 1. Okay. So it looks slightly better. And now at this moment, we can even apply we can turn these values of this image into the integer values. And after they are integer values, we try to use histogram equalization. So histogram equalization, what it does is that it spreads the histogram of a certain image, and finally we can observe, okay, I think we did not run these, but it's not super essential to run these two. But then we need to compare. Actually, this comparison, okay. So here we're just trying to check actually two different histogram equalization functions, but let's see. So this is II. Let's plot it, not to compare in show II. So finally, we get such an image. Now let's check again how where did we start with this image. Initially, we had this. Okay, this is the image which is given to the medical practitioner. Okay, and now the using our algorithms in medical imaging is the most challenging problem. It's also the most vital. Is also the type of problems that have the highest impact that one can do with image analysis or signal analysis. So we started with this image, then we applied the high pass filter, we got this, so we got only the edge, most of the edge information, but we lost a lot of other information. Then we modify this high pass filter as we lifted this a little up, we get this. Then we use histogram equalization and we got this. So when you compare all of these steps, it looks like to an observer or to a medical practitioner, this information, it was here, okay, it was here. But now it's visible to the human perception much better here, okay? And now there are two things. The computer knew that this information of these ribs, protective ribs that protect the lungs, the information was there, but human perception was a little worse. Now, when we get this final image here, we have changed slightly, we've changed a lot actually regarding the pixel intensities. And in fact, in this final form that we have this image here, not only it is better for human perception, but it's also better for computer, which means that if we want to quantify something with regard to, let's say, to the size of the ribs, because this is the only information we can acquire from here, okay? Or if we want to observe some degradation of the ribs, even the computational techniques would perform better on this improved image. It will perform better here in the fourth version when compared to here. Okay, so it's not that only the human perception is improved, but also the algorithms that we can apply in the first one versus the fourth one, they are going to perform better on the last one. Okay, so this is really and that's why we use the filters. And the filters do change the image, but they change it accordingly of how we want it to be. Now we can check a couple of other tasks, not tasks, but just for a moment. Let's see that. Let's assume once more that we have this I. Okay. I'm afraid I might have. Let's see. This is the modification here. I0 HP2 evaluate selection. Now, we re-evaluated, we can see it from here actually, this I, the image which is scaled from 0 to 1, and this image which is scaled from 0 to 1, we convolved it in the Fourier domain or in the transform domain with this filter H1, which was not 0 at the center. And now, let's see if we observe some improvement for once. Let's say im show I, the image from 0 to 1, plus image from 0 to 1, high pass filtered, but the second one, okay, so we are just adding these two together, and let's see if we get something better. Okay, we got this image, and what we did here, we just added up on top of each other the original image, which was this one here. We added with this very last here, and now we can judge whether we are to some degree better. In fact, it looks like this has more, but we don't. Wait a second. We have not done this one histogram equalization on this one. So let's do that and let's see what we get. So we just manually added the original image with the high frequency term. So now what is the logic behind this one? The logic behind this one, it can be this, that this is the image itself, and we are just adding some edge information. Okay, so we are adding the highest frequencies, which means that enhancing sections that we care the most. But let's do also one final thing. Let's do this figure 1112, which is a subset of the previous one, and im show histogram equalization. Let's see if we how does this look like. So this 112 and the previous one it was 111. Now, of course, this looks much better, this one, okay, which is now histogram equalization of this image. But now let's compare with this previous one. Now, with human perception, it's hard actually to reach a final verdict, which one is better. But I observe that, okay, so here we have lost some information. Here it's more intact. So it looks like this is a little better. So just adding those like that, it was not the best option. But now, you can run these codes later on also on your own. And just for a moment, let's change this factor from 0.75. Let's put it, and okay, this is 0.5. We can make this 0.25, so we can put less of those. We can put much more components of the high frequency terms. And regarding this, probably it is best if we, wait a second, no. I'm afraid if it's better if we do this clear all, so the variables are gone. Then we read the image that we want to analyze, the X-ray of the chest. We scale it from 0 to 1. We need to know the size of the image. We find M and N. Then we have to, we need to construct this filter with a radius of 70. Okay, we need this. We can even change this slightly. Okay, so if you want a high pass filter, that means that we can make this slightly narrower. Okay, so let me test this one for a moment, which means that what are we really doing? So by narrowing this 55, that means that we are going to get more of high frequency terms. Okay, we are getting closer to the center. Okay, if we draw this graph, you can really let's see what we do. We could have done the opposite actually, but okay, let's test it now for the moment. We found this filter H, but it is 0 at 0. Then let's modify this one as we explained this on the board, where H1, it will be slightly better than the previous one. And now that we have a modified filter H1, let's convolve with the image in the Fourier domain. And finally, let's see, let's do this one 441 so that we don't mix The previous one, it was 41, okay? Image selection. So let's see what we have gotten. So the previous one, it was image 41, and we have to compare those. Let's hope we find them. Where is an image which was 41? This is 41. And now, with this new filter where we enhance the highest frequency terms, this is what we observe. Is it really better? To me, it doesn't look better. And actually, we can also apply this scaling up from 0 to 1. We can show this. Now, it takes some effort actually but I'm sure in scaling we convert them in integers. We use histogram equalization, and finally, let's see. This is 1411, and finally, let's see what we get. But of course, this is what we have now. You can always run this again and have a look actually, and you can choose on your own. Is this way better than what we did before a while? And probably this could be better if we bring a medical doctors. They might even argue saying that this is much better because the density of the bones right at the junction, it's much higher than the density of the ribs, not bones, far away. So they might give a more qualitative evaluation. But this is something that we try to figure out. Not that one image analysis that we try to enhance it by using a couple of modifications, which one of them was modified high-pass filter, the other one was histogram equalization. Now let's move further, and we have here in scaling I. Let me try to remember. Okay. So in fact, all of these steps that we put so far, we can define a function where we get the function, and this is correct. We just wrote this here, and this function here correct, which means that correct the image. You can also what this includes here. It's the same all the tasks that we did just now for a moment until now. We read the image. The image is scale 0 to 1, we get the size, we apply the high-pass filter, we define the values of K1 and K2, we modify the filter here. I think all of these steps, you already saw them, and as a result, we get the improved image is equal to the image high-pass filtered in integer domain, okay? And you can run it simply by running this function correct I. Now, this function, which is in this part, this is also put in one piece of code here. Maybe we can, here, sorry, not this much. So yes, we can, because it might look better. So this function now, it is not that scary. Actually, it's much better if we write it like this. Now, this function, we have defined K1 and K2 in there, but we can also denote another function where we can call this on correct2, where the input is the image, D is going to be the size of the high-pass filter, which is this D. K1 and K2 can be these parameters which were entered here manually, okay? So you can read all of these, you can get any image, and for example, let's see. Let's clear again these variables, and let's close a lot of figures that we have plotted. They absorb a lot of power and a lot of memory. And let's see this other image that we have here. Evaluate selection. We read this image. Here we have an image which is composed of many cells. And by the way, actually we can even do this one like this. So this II, we can do it. Sorry, II. We can select 1 to 500, 1 to 500, because this is pretty large image. Maybe we can have a smaller one. Is it going to override? Okay, it did override this one. So this is how traditional cells look like. And on this image, which is now smaller, we can apply this correct function. And we can apply this right away like this. Evaluate selection. And, sorry, okay. So now, if we do just an analysis roughly, it might, when I say roughly, qualitative analysis by using only human perception, it might be difficult to reach a conclusion, but we may have to look for specific features such as this region here, or let's bring this region on top of here. Then we can compare this with this, okay? And who knows, maybe it's better. There is one major way to check this one, which would be the best way to check this one is to have an algorithm which does any kind of quantification in these images and run the same algorithm that does quantitative analysis, run it on both of these images, the row one and this one here. Now, similarly, we can have here an improved correct 2. We have this image as an input, this 140. What was this 140? Let's see here, is a D. So is the width, but since we crop this down to 500, let's have this one even 40. And the K, let's use this one 0.5, K1, and K2, let's use this one 0.9. And so what this is going to do is going to this function is going to construct inside it itself the filter, and the filter will be applied to the image that we put, evaluate selection, and okay. This is the answer. And again, it remains upon us to check which one is better. Okay, so we have 3 now. It might be hard to figure out. Maybe we can crop much smaller regions and we can observe, for example, if this one, to me it looks like the original one is much more better, if I'm not wrong, okay, at least, but I'm not exactly sure. So we can look at this region. Is this more distinct here? This remains to be seen. And let's see if, for example, we have the original image, it's II, and we can also do the following. We can say figure 672. We can say here, show the original image II minus the improved image 2, and let's see if we see anything. It looks like if we subtract the original image, which was this, okay, from this one, we subtracted not this, but sorry, oh, okay, actually it was this one. We subtracted this one, and we did the subtraction in order to observe visually, not by reading all the values in the matrix, but here it looks like we have a major difference, and the major difference, it looks like it is in these edges here, okay, which is much brighter here. And here we have, okay, so it looks like we have very high intensities. Now, when we analyze these images, it's also good to use a little bit of intuition and a little bit of general knowledge. So in fact, these bright regions that are also seen here as a difference between the original one and the filtered one is just useless piece of information, because the microscopes, when they take this image, there is an artificial high reflection at the edges of these cells. Okay, so what one can do, in fact, is that we can suppress the highest pixel values, which means that we can suppress these super bright regions. Okay, but how can we suppress those? We can narrow down the histogram of the original image, and we might get much better. Now, let's move to another example. So this is the application of these filters that, now let's see, for example, let's assume that now we're talking about, let's see, we'll try to go over what we have here, like one does not exist. Okay, so we have here an image, which apparently we don't have it, but let's get another image, which is here. This is, what does it say? Does not exist. No, it looks like we don't have it, but what we can do is that we can read this image here, which is all shapes. So we can have here I is equal to im read all shapes.jpg. So we read this and we notice that this image is RGB, which means it has one layer for the red contribution, for the green and for the blue. And this is a color image, and we can see that this one, figure 1, im show I, this is what it is, okay? And from this image, we may be interested into checking. Well, first of all, we may be also interested into binarizing this one, or which means that we have them 0 and 1. And often, when we find these feature descriptors, we define the background as 0. It's also a little bit intuitive. Okay, so if we make the background 0, the object itself will be 1, this would be the binarization. And in fact, probably I might have this prepared here. So actually, oh, here I have it. So we can read the image, read. Actually, we just run this one, and we have the same variable. So we can see here it's 1500 by 1600 by 3. We can convert this one to grayscale, and in grayscale, now this is it's only 1500 by 1600. Then we can binarize this one. Okay. So we binarize this one, and this is now logical. And when we try to this is I trace. So this is I. In fact, this I, let's check what this is. Figure 11, im show I. It's all here, but maybe it's better if let's define I is equal to I from 1 to 400, 1 to 400. Okay, this was too much, and let's see. Okay, so apparently we just got 1 square. Okay, and probably we can remove this word square from here, so we can have this. Let's have this one to 350. Okay, we remove the word square, so now this is the image I. But now, if this is the image I, we can we said that we want the background to be 0. If we want the background to be 0, we can do here figure 12 and im show not I, so the negative of this image, and figure 12 is this. So we may be interested to analyze this image. Now that we have this, we can identify. So one of the major important elements is to be able to identify the borders. And these borders, there is this function boundary tracer, which defines, if we look this as a variable, this is a cell, and this cell is composed of, if our image has many objects, like 11 objects, then we would have 11 different cells. The first cell that we observe here is, they are all the coordinates x and y for this square that we have, and then we can see here that the b itself, let's see what this b is as a variable. So as we see here, b, it has one full column made of x values and one full column of y values. Okay, so if we check for the size of b, size of b is 1496. And in principle, since this is defining the edges, it looks like the perimeter of this object is 1496, this pixels, okay? So we can quantify it like this, and we can also say figure 10, im show I. Let's see this image now, what this is. We know, actually, okay, it's not I, actually, it's not the negative. But okay, I think we may get a problem here, because since the background was white, we might get something not where what we're really, you see here, so this is something wrong here, because we have identified, it looks like the white region, it looks like an object. That's why it has circled around like this. But probably somewhere here, because we did the manipulations down here, maybe it's best if we rename it in here. We say I is equal to not I. Okay, so this is all that we need, because we did not, and then we can run the rest only by changing the figure numbers probably, and this would be B would be overwritten. And let's evaluate the selection. So it's going to be the same thing, but the region of interest now is this boundary, which is defined in blue, which is the object now, which is white on a black background. Okay, so this is what else we can do is that we can get something that we mentioned before a while, which was to get the signatures. And these signatures, they are the plot of the radius as a function of theta that we wrote it on the board, okay? So we have two coordinate systems, and actually this is like, there is something in complex mathematical analysis, which is like differential topology or differential, what's the name, differential geometry is also called, where every point of a curvature is defined with one coordinate, with only r and the theta. Okay, it's a more generalized coordinate system than Cartesian coordinate system. It's a better one. You can do much more operations, and we always know that as we close these and if you clear these variables, we always know that more generalized concepts or tools produce much more results, and we're lucky that in this course, we are also trying to draw, we're trying to read two different objects. Let's see how they look like. And we're trying to identify them by determining the radius and the angle theta. So here we have two objects. One of them is a square on a black background, as it is. The other one is rotated. And we can define the boundaries, okay? So for both of them, so once we define the boundaries, this is a function which determines the boundary signature. Now, this boundary signature, this piece of information, this will carry the angles r and the theta. So if we evaluate this selection like this, the r and theta, so let's see what is ds, dr and ds, and I think, so this is the signature of the first square, okay? Then the signature of the second square, it's here. So you can see that they are not on top of each other, and because of this rotation, the shortest radius does not correspond for the same angle theta, okay? So for example, we see here that we have a maxima, this in blue. If this is in blue here, this means that this is the square that was rotated, because when the angle theta is 0, we have the farthest edge, which means this in fact. So this point in blue here, which is 170, this corresponds to the distance from this center to this farthest edge, and then it becomes shorter, it becomes maximum 170 again at an angle of 90 degrees. So here we see that an angle of 90 degrees, that's what we see. So in this, using this technique, we can analyze a large object with a lot of small images in there, and we can try to distinguish their features, okay, how they are with respect to each other, how they are, what angle are they constructing. Now, let's see, let's try now to describe also the Fourier descriptors. Now, this was signature descriptors, they are rotationally variant. Now, let's see, let me see, first of all, if we have this specific image, letter C. No, it's wrong. So let's pick up the C here, letter C. And the letter C's are, the letters are very difficult to save images. Now it's a hard task, so let's call this letter C JPEG. Okay. So the letters are difficult. So if I ask you what is the, can you write the letter C me shkrim dore apo me shkrim shtypi, kam frikë se një pjesë e jona këtu në klasë shkojnë se me shkrim dore mund mos ta bëjnë të saktë. Që do të thotë çfarë klase jeni ju? Okay, so let's see here. So we have I, apparently we got this letter C. Apparently it's a color image because but before we do that, let's clear all variables because we need a workspace not to override similar elements. So we close all figures and let's read this. The second code is not going to work, or it worked actually. I did not expect it to work because this is RGB. Maybe it's best if we convert this one to I is equal to RGB to grayscale of the original image I, and we don't need to print the values. So we evaluate this one, and actually let's see what this is. Let's show this one. So it looks like it's a dark object on a white background. So in order to check the boundaries, we want the background to be 0, which is both intuitive and also that's how we want to do it for now, okay? So that means that, let's say I is not I, evaluate selection, and figure 11, it's gonna be something like this. Oh, that's interesting. So we observe some elements which were not visible before a while. Why is this? Why is this? Well, in order to improve this one, so we got RGB to I, we can say here I is equal to im binarize. I forget sometimes how we can write this one. So we can, let's say that this is I im binarize, so but no. I think it's best if we read this from scratch because, okay, now we have the original image. Let's binarize it, evaluate selection. Now that we have binarized it, let's see figure 12, im show I. Okay, this was good. But now let's get I is not I. And now let's plot this figure. And we expect to not see imperfections, but we still see them. Why is this the case? This was logical.
You have to change I bind.
Sorry? Oh yeah, okay, thanks. I forgot it. I changed this, okay, thanks. So that means that we binarized it. Then we have to say here, not I binarized. Okay. That was wrong. Then let's do this 14. And I hope we're going to be lucky this time. Okay, that's better. So let's see what we did so far. So we started with this image. I think we started with this one, but when it's best once we binarize them. That means that we put a threshold, and anything which is brighter than some value, we call it 1. If it is anything which is darker than some threshold, we call it a 0. And finally, we get this. So now our problem was this: that we were not getting this. Actually, 14. This is the last one. We were not getting this, but we were getting these. Okay, but it looks like we fixed it somehow. Not somehow, but we fixed it. And now on this one, we want to determine the boundaries. And the boundary is better if we do it like this. Now, once we identify the boundaries, what we do is that we need to identify the Fourier descriptors. Now, the Fourier descriptors, it's a simple, not simple, it's just an operation, which in principle, what it does, it multiplies all the boundaries with plus minus 1, because we know that when we go between the Fourier transform from the real domain to the Fourier domain, we always have a FFT shift, okay? So we do an FFT shift, and when we do this FFT shift, that we shift these graphs, and actually a review of what I'm saying right now, I think you can do it in some advanced mathematical course, but I guess in our course, I think we might have covered this one, where we observe that this shift is necessary. And once we do that, we just apply the FFT transformers, okay? So I think I had the detailed code of this one, but probably it's in a different function. But let's see. We read the image, which was the letter C. We determined the boundaries. Okay. It looks like the perimeter. You see the size of B. That letter C that we read, the perimeter is 1029. Okay, 1029. That's the perimeter in pixels. Okay, because those are all the coordinates for X and Y. Okay, that's what we have. And now this letter C, we need to find the Fourier descriptors. So the Fourier descriptors, so okay, we have a lot of them. So how many of those do we have? It looks like we have 1030. So it's one more than the B. In fact, this is the case when we have a boundary which is an odd number. The Fourier transforms, since it wants a symmetry, what it does, this 1029, it's added an extra line. So the last line is duplicated, and we make it 1030. Okay, it's good that by coincidence we got this. But these are the Fourier descriptors, okay? Now that we have these Fourier descriptors, and let me say also what these Fourier descriptors are. Imagine for a moment the following. One of the most important functions that we use in signal systems is the Euler identity, which denotes that e to the power I theta, this is equal to cosine theta plus I sine theta, okay? Now, what is this? The union of all of these points, it defines a circle, okay? So in principle, this is like you have one parameter here, one parameter here. So with two Fourier descriptors, we can precisely define a circle, okay? So if an object is much more complex, we need a lot of Fourier descriptors. But let's see now. So we found the Fourier descriptors, and we can also take the same way that we take the inverse Fourier transform. So let's not forget, we had B, which was the B, it was original, what do we call this? Original perimeter or boundary, actually. Boundary is a better word. Now we have Z, which is defined, so this was B, right? This was B, it was original perimeter. Now Z, it has the Fourier descriptor, descriptor. Now we can take the inverse of this Fourier descriptors, we can find B1. So B1, this we can call this one reconstructed image or reconstructed perimeter. And to do this, so let's see, Z is a Fourier descriptor. We have here B1 is here. So B1, here we have it. Now notice that B1, we always argue, we try to prove to anyone, to any user, that B1 should be equal to B2. Why is that? Because we should be able to reconstruct the original image that we had. But the first inequality between these two is that the size is not the same. Okay, you see B and B1, one is 1029, one is 1030. Now we get this, and let's see for a moment what is this figure which defines evaluate the selection. Matrix dimensions must agree. You see, this is right. We mentioned that one. Probably is best to do the following. So I think we know this already. What is the size of B? It's 129 by 2. And let's define that B1 is equal to B1, but we select from the first row and from 1029, because if you see here B1, it's 1030. But we want to pick up only these rows and all the columns. And now B1, it's smaller. You see here, it's now 1029. And now I think we can check what would be the difference. Actually, this is not very smart for one major reason. I said this is not very smart for one reason, because B1, B and B1, they are just two columns. And that means that if you zoom in, we're going to have an image which is 2 pixels wide, okay? We don't see much when you have 2 pixels wide, but if we zoom in, like this. Actually, this is not smart when things are like a vector, but we can do the following: clear screen. So we clear all the screen, and then we can do b minus b1. So b minus b1. We claim that they should be equal to 0, okay? And we notice that these values that should be equal to 0 is like 0.04 and so on. But if we climb up and we look at the beginning of this whole matrix, what you observe is this, that all of these differences, they are multiplied by 10 to the power minus 12. So this is almost 0, okay? Since we are dealing with numerical analysis here, or when we talk about the discrete values, we might not expect infinite precision, which means that the difference between two quantities that are double and they have Fourier transformed, we don't get integers each time, right? Because the only values which have infinite precision are integers. And when we transform from Fourier transform, from inverse Fourier transform, it's very hard that the domain and the range are all z, are all n, or z, which are integer numbers. And so I think we are clear in this one. So there is a difference, but it's almost 0 because this is what, so that's how much different they are, which is almost negligible or invisible. Now, we had the letter C, and we say that, now let me see, let's do it also just for a moment. By the way, let's do clear screen. What is B? B is this, okay? It's an array of numbers. And now, what is B1? If we pick up all the rows of B and the first column, this is it. We get all of these 7s, right? If we pick up all the rows of B, which we denote like this, and only the second column, we get this, okay? So this is the X and Y. So if those are X and Y, we can plot them as if we are plotting a graph. And this is what we see, okay? This is the letter C that we initially received. Now, what is this? If we exchange X and Y, the graph is going to look like this. No, we got the same thing. Okay. Figure 22, 23. Let me check. Okay, no, what I intended was to do this. We do this 2, this 1. Okay, and let's plot this again. Okay, figure 2, 3, here we got it. Okay, so it looks a little better because we know the C, what was it initially? Okay, it looks like we have even rotated it by 180 when you compare the initial one with this one here, but we can solve this one a little later. Now, here we are, and let's not forget that we had an image B, which was the original image, and we had the image B1. What was B1? B1, it was, we had this path, we had B, and then we found the Z, which is in Fourier domain, so B, it was a function of X and Y, right? Then we use the Fourier transform that we call this Fourier transform. It was Fourier Descriptors actually, which are now U and V, this new variable. And then we apply the inverse Fourier transform, and we find this B1, which is now X and Y, but they were very close to each other. Now, this is what we had, and now so we just want to convert figure 24. This is the B, and most probably the BB1 is not going to be evaluate selection. So to anyone who tries to qualitatively, with human perception, to check any difference between those, it might be relatively difficult because, as we said, the differences, they are 10 to the power minus 12. Now, let's see, what do we have here? Check the result below. Let's see what is the difference. Okay, so we had this letter C, right? And this was JPEG. And for a moment, let's clear all and let's close all. And actually, I think, okay, we need to add a couple of steps here. So we evaluate the selection. We need to make this one RGB to gray because it's 244, 218 by 3. We just convert this one to So we lost the 3, and now we say I is not I. I think this, we needed this, and this all is good if we do figure 1 show I. Okay, same problem like before, but we can solve it as we did it in here. So again, actually, I hope everything will be fine, but I think we should be. So far we read these, and we override I. We make it not bin. Okay, now we should be good. I think we were here, right? Yes, yeah. So what we want to do here is that we have that image I, okay? We want to determine the boundaries, and we find the Fourier descriptors. Now, the Fourier descriptors is composed of a vector which has 10, 30 values. Okay, so this has so many inputs. This is how many coefficients that these Fourier descriptors have. Now, we want to apply the Fourier inverse descriptor, but not using 1030, but using only 4. Only 4 out of 1030, okay? So now, if we had a circle, let me say this one, if we had a circle, we would reproduce the circle if we had only 2 here, okay? Because circles, that's how many Fourier descriptors they need. But in our case, we don't have a circle, it's slightly different. So what we are trying to show here is that we have that image, it has specific size, we find the Fourier descriptors, it's a vector which is composed of 10, 30 coefficients. And now we want to produce B4, which is the reconstructed image, where we use only 4 Fourier descriptors. This is a reconstructed image using only 6, and this is a reconstructed one using only 70. Okay, so let's run all of these, evaluate the selection. And so here we have all of these, and we want to convert all of these into images, such as MN, we know what they are. I think we have run that part of the code. We evaluate the selection. Where are we stuck? So it looks like MNN. So I, it was 244. Why this N jumped so high? What? We have a problem here, which we can solve it just by doing the following. So M and N, we evaluate this, so now they are correct. I don't know why this N was so high. So that means that we have to okay. Subscript, what does this mean? Subscript indices must either be real positive integers or logicals. Boundary to image 4E. We have to solve this problem, which means that this B4, let's see what B4 is. B4 as a variable, it's okay, wait a second. No, but this should not be a problem. So B4, okay, it's going to be a lot, okay. B4 is like this, okay. And this is saying that subscript indices, but we are good. This part, I don't understand. BB4, wait a second. BB4. What if we do it like this then, just for a moment? We have this B4. We can do the following. Figure 11, plot. Let's plot here BB4. All rows, second column. BB4. All rows, first column. Why? Undefined variable function db4. Okay. Oh, okay. We did not even run. We could not even run this one. So we have the Fourier descriptors inverse. So we have b4. Wait a second. So I think we can even do it like this. Sorry, this was because this is in real domain. So let's remember something. This z, this is complex domain. Okay. So we're talking about the numbers here are 3 plus 4 times I. But this b4 or this b6, this is real domain. So we have taken the inverse Fourier transform already. Okay. Since we inverse ft, we do the inverse Fourier transform. So actually, let's see again. What do we get here? Oh, okay, we got it. Okay, fine. So we are good. So that's what you get for C, okay? We had the letter C, and that's how what you get if you use only 4 Fourier descriptors, okay? It doesn't get any better. For a moment, actually, can we, let's put here, hold on. Let's put here, hold on. And let's plot on top of this one, let's plot the B6, which is composed of 6 Fourier descriptors. And now we need only this. Okay, so this is, initially we had this letter C, which looks like a B, which is in blue. Now that we use 6 Fourier descriptors, we get this. Okay, so it's trying to get close to a letter C. Okay, so let's put here hold on, because we need it, and grid on. So this is how it looks with the grids. And now let's try to recompose this one. When we have here 70 Fourier descriptors, I believe, oh no, okay. Okay, I was afraid I should not have written this figure 111. I thought I needed just to plot this one, but things are good. So here we observe that with only 4 Fourier descriptors, we constructed the letter C, this line in blue, which it looks like it's not very correct. And then with 6 descriptors, we got this boomerang, okay? We got this orange color, boomerang-shaped C letter. And when we use 70 descriptors, we got this other C here, okay? Which is, let's see how close is this C, and the details is in the edges. So let's see for a moment how much different is. So if you observe this, we have some imperfections here, which, so one reason can be that maybe this is damaged. I don't remember whether we applied that in binarize on time, but anyway, so what we can do is that we can have, this is with 70, and we have, let's do this one with 700, okay? Let's have a B700. We have the Fourier descriptors, the input is Z. So this Z, we know what this is. This is composed of 10, 30 coefficients. Let's use only 700 of those, and let's get this B700, and then let's plot this, sorry, B700. Let's keep here, hold on, just for a final time. And okay, we need also this. And if we evaluate this, not this. Now, okay, it looks like the new plot, if you can read, see carefully, the edges are more straight, okay? So the 700 pieces, it made a more, so if you see here, the edges are not curved, okay? They are edgy. Their angle could be even 90 degree here. But here, in the previous, when we had only 70 Fourier descriptors, these were curved. But now, it looks like the update that we did is a little better. So we see here the edges, which we observe here. Good. So this is how the Fourier descriptors try to reproduce an image, and that's what they do. And the idea of the Fourier descriptor is that it, for any input, it multiplies +1 - 1 each time because of the following reason that we have mentioned before some time. If you remember, when we plotted on the graph the high-pass filter and the low-pass filter, we said that the 0 is in the center. So on one side, we have the negative values, and on the other side, we have the positive values. And this is what we do. If we have a boundary which has different coordinates, We multiply the first with 1, the second with minus 1. 1 minus 1, 1 minus 1. In the end, we're going to shift those. And this is in the domain we are going to play with those. But finally, time is passing by. And I just want to confirm one little thing regarding something. Okay, sometimes I forget my microphone or I turn down the voice. And desa që mund të keni një koment, më ka ndodhur, kam humbur një herë çerek orë ose 10 minuta duke fol në vetën, se kisha ulë zërin e kompjuterit. Edhe thash studentëve, po kur ankuta gjatë as u përgjigja, kishte marrë më mirë në telefon 112-ën, se ato mund ta kishin zgjidh problemin. But we are good. So okay, so I think let's see, for example, what we have here. So we have this specific image, and we have these all shapes. So these are all the shapes that we have, and I have extracted here from the all shapes this one at the bottom. Okay, in order to extract this one at the bottom, apparently this is black. I did by selectively selecting these rows, 1044 to 1400, which is some bottom region here, and the columns 1216 to 1600. Okay, so finally it looks like I have this image I, which is not, so let's do this one. I, let's override this one, is equal to, oh, but we have not binarized it, I guess. No, probably it is. No, it's binarized here. Okay, so we don't need to do it. So we have I, not I, and we don't need to print all of these, and also all of these, and value selection. And now on image 84, okay, so this is what we are more looking for. We want the background to be black, and we want to analyze this image. Now let's run here from line 170 to 177. So the image 160 to 177, which is somewhere from here. We need to know also M and M, so the sizes, because we need this input, MN. This is equal to the size of image I. Okay, so we need this input, and then we go ahead and we say that, okay, I've changed something because I've changed the code a little bit, but where can we start from? I think we need to start around here. So we're at the letter, we had it, okay, I think we start from here. So we have the letter I, we need to identify, and let's not forget we are dealing with evaluate selection. Let's not forget we're dealing with this image now. And we find these coefficients, and we want, let's do this 70, and let's see that shape. If we so we have the Z, okay? We have all of these coefficients, and we want to use only 4 coefficients here, which is going to be here B4, and this B4 and the last figure, this was figure 84. Let's do this figure 85. This can help to lead the eye. So, okay, so apparently from such a shape, that's what we get with only 4 descriptors, okay? We get a circle. If we did 2, actually it would be interesting if we do just 2. Let's see here, let's use 2 descriptors and let's call this one so that we are not confused with 2. And this is 2. No, maybe it's best if we kept it because we have not run this yet. But we have B4. Okay, let's run all of these actually because we will need these. Evaluate selection. But, and then, so we have B2, B4, B16. Let's plot B4 again, just for a moment. And let's plot here, hold on. This is figure 86. Okay, so we plot the before, and we did hold on. And let's do here B2. Let's see. Okay, we see that B2 and B4, they are slightly different, okay? And they should be because it looks like B2, it can construct a pure circle. B4, it's adding some more to it. And now let's try to plot everything on the same thing, on the same figure. So let's see what 6 can bring for us. 6 is still on top of the 4, okay? So we don't see much improvements. And we're looking to get a shape like this, okay? And let's see what the 70 does for us. Okay, it looks like we have run it for 70 feature components, Fourier descriptor components, but the name of the variable, it is 700, so this should be 700. Okay, we don't see much. Okay. So somehow we cannot plot it on top of those, but it looks like we reconstructed better this specific shape by somehow compressing the data because we received the same similar object with much less components. Okay. So this is what we can observe for the feature descriptors, and we saw just random signatures, which were boundaries defined as a function of r and theta. We saw also feature descriptors, and now I guess the last time we had class, we did not we did not see this moment invariance. When you did the first homework, I remember one of you, it was Edith, the review papers, they were about moment invariance. And I remember those papers, and I remember even the review that Edith wrote about these papers. But what they were talking about some mathematical values which can be associated with a figure and trying to get specific and trying to compare those, okay? And in order to compare those, we can calculate the moment invariance. Now, I can leave this as a homework for you, which would be, you are going to get this code, and I'm going to provide you also a couple of images. And what you can do, you can generate the moment invariance for this from these specific images. The same way that we observed some feature vectors, which were very long, okay? Now, this moment invariance are going to be slightly smaller, but one thing which is essential is the following. Often, in any class, I often ask the students to plot the dependency of a y variable, which is, for example, I try to ask this question, and engineering students have difficulty to figure this out. I say, plot y is equal to 1 over x. But x, it starts from 10 to the power minus 5 to 500, okay? Can you do it? And when I ask this to the students, often I get a line which is merged with the x and y coordinates of the Cartesian coordinate system. Okay, so we can try it like this, actually. So we can say x is equal to lin space from 0.001 to 50. Okay, this is x, and y can be equal to 1 over x, okay? And the question is simple. I say, plot for me, plot figure 44, plot x and y, okay? And I say, I want to see the dependency. So this is the answer, okay? And now, the thing is that I say, I don't see the graph. I say, oh, professor, I plotted, but I don't see it. Imagine now if this is not from here, but if x, it's from 10 to the power minus 11, okay? Nobody can stop me to do a question like this. And maybe I can put here 500. This is x. The y is here. And the figure 45 is going to be the following, plot xy, okay? Now, this was 44, this is 45. So this is, I can see nothing. So in this case, how can we make things visible? To make things visible, the best thing is to plot logarithms, okay? Because we are not losing the information. But let's see, we can plot the following. Log x, actually, which one is more drastically changing? I think this is good. So you see what we observe? I don't fully understand this one for the moment, but we can even do here log of y. So now things will look much, much better, okay? Oh, no. Of course, we have to reply to the message. Okay, so this is the plot, xy, that I was just trying to show, okay? Now, why did I explain this? I explained this because often the quantitative values that we get for moments, they are changing in several orders of magnitude. I remember in the first two sessions of this class, we defined moments for images which involved the average of the pixel value, which was the center of the standard deviation. We defined the standard deviation, which was the width of the histogram. We defined the skewness, which was the third moment, which checks whether the Gaussian distribution is non-equal with respect to the center. We defined the kurtosis and a lot of these parameters. But these parameters, they are not in the same scale. So if the average of the pixels is 10 to the power 2, the skewness, it can be 10 to the power minus 3 or 10 to the power minus 4. So if you want to plot a vector like these, quantities that are changing a lot, you cannot see it, okay? Or they will be negligibly different from each other. So this graph here and this graph here, they are the same, okay? Just that I'm changing slightly the way to see it. And the engineering student should be very smart to be able to draw this, okay? So if you give this to submit this one, well, okay, fine, but I might not even see this if it's too much close to the y and x, z axis, okay? This is empty. But now, so see, now with all this explanation, we need this because when we find this moment invariance, we can use a transform, which is here in line 233, which what it really doing is doing the following. So a feature vector, which is defined, which the result of this code is this, okay? We get this phi, okay, moment invariance. And we get a lot of zeros here, 0, 0, 0, or 0. But we can use a transform on these values, okay? And the logic is equivalent, not exactly equal, but is equivalent to what I was talking before a while, which I was saying that if you plot the logarithms of two quantities, which are drastically changing, we can make them visible, okay? So when you find these descriptors, since they are changing in a few orders of magnitude, you just apply any operator like this. Okay, here we see like we use the sign of these values, okay? So let's say, for example, just for a moment, I don't need to run this one. So if we evaluate this one, sorry, what is it saying? MATLAB expression. I don't understand. Maybe MATLAB wants a comma, not a dot. Okay, we can check this later, but we know. So I'm going to give, so this will be your homework for next time, okay? So you're going to run this code and compare different image components by comparing the moment invariance. Now, I want to give a break, but if you have any question for what we discussed today, we can go over your questions, okay? So I strongly suggest, well, to read chapter 12 from the textbook, and if you have any other question, you can always come back to me. So these codes will be, of course, I will share them with you. Now, okay. Do you have any question? Okay, if not, then Dedioba says yes. Okay, so if this is all, I think we can close it now.
Goodbye, Professor.
Bye. Have a nice day. Have a nice night, actually.